Hey folks, welcome back. This is Unit 6. We're going to talk about arithmetic sequences in this video. We're going to talk about how to write an arithmetic sequence using explicit or recursive formula to model a real-world context. We're going to talk about how to rewrite a recursive formula using an explicit formula or vice versa. And we're also going to talk about how to write an explicit formula, define a recursive process, or complete a table of values that can be used to mathematically define a real-world context. Okay, so let's explore. Go ahead and read this. Okay, welcome back. So we notice that we're adding $150 each day. So on Monday, they're offering $150. If no one answers correctly, on Tuesday, you can earn $300. So on Wednesday, if no one answers on Tuesday, you could get $450. And so we notice that we're adding $150 each time to find the next term. And so we can continue going like this until somebody wins the prize. This is called an arithmetic sequence because we're adding 150 each time. We start with 150, and then we add 150 to get the next term. A sequence in general is a set of things, usually numbers, that are in a specific order, and each term is a number in the sequence. So for example, 3, 5, 7, 9 is a sequence, and specifically this is arithmetic because we're adding 2 each time. 3 is the first term, 5 is the second term, and so on and so forth. We also refer to terms as elements or members. They mean the same thing. And these 3 little dots here just means that it goes on forever and doesn't have an end. By definition, a sequence of values follows a pattern by adding a fixed amount from one term to the next. And we refer to that as an arithmetic sequence. So which of the following is an arithmetic sequence? If we look at this, we notice that we're going from 3 to 6 to 9 to 12 to 15. So the question is there a constant change from one term to the next? And so when we look to go from 3 to 6, we add 3. To go from 6 to 9, we add 3. 9 to 12, we're adding 3. So this is indeed an arithmetic sequence because we're adding 3 to each term. If you look at this next example, if we look, it might be a little bit more difficult, so we could actually work backwards and we could say, okay, well if we do 9 minus 13, we get negative 4. So is negative 4 what we're adding? Or we could call it the common difference. So if we add negative 4, we get 9, and then negative 4 would be 5, and then add negative 4 to get 1, and add negative 4. So indeed, that is another arithmetic sequence. Is this an arithmetic sequence? Well, to go here, we have a difference of 3. And from here to here, we have a difference of 5. So this is not an arithmetic sequence. Here, we have a difference of 2, and then a difference of 4. Not an arithmetic sequence. Here, to go from 21 to negative 16, we have a difference of 5, and then a difference of 5, and then a difference of 5. So if we add 5 to each term, we have an arithmetic sequence. How about here? Well, here there's a difference of 90, and here there's a difference of only 9. So since the difference is not the same, it's not an arithmetic sequence. So how could we find missing terms? Well, we know we have to have the same difference between every every consecutive term, meaning that to go from here to here, we have to add some value. We'll call it x. And to go from here to here, we have to add another value. Well, we can actually write an equation. So really, what I'm saying is that if I start with 4 and I add x, and then I add another x, I should get 22. Well, now I have an equation, don't I? So now I can just do 4 plus 2x equals 22. So 2x equals 18. So x equals 9. So my common difference is 9, which means if I go back to my original problem, 4 plus 9 is 13, and 13 plus 9 is 22. And there I have my missing term. I can do the same thing even if I have 2 missing terms, because I know to go from here to here, I'm going to add x. So if I start at 100 and I add x, and then I add another x, and then I add another x, I'll get 82. So really the equation I'm looking at is 100 plus 3x equals 82. So if I subtract 100 from both sides, I get 3x equals negative 18. And if I divide by 3, x equals negative 6. So my common difference is negative 6. I go back to my original problem. So 100 plus negative 6 is 94, plus negative 6 is 88, plus negative 6 is 82. And there are my missing terms. One more time. We can even do this with decimals. So if we have 80 plus 1, 2, 3, 4 x's, I should get 93.2. So if I subtract 80 on both sides, 4x equals 13.2. Divide by 4, and so x equals 3.3. So now I go back up, and from 80, my next term will be 83.3, and after that I should get 86.6, and then 89.9, and then 93.2. Okay, so go ahead and try these. Welcome back. Here are your answers. Okay, so what did we do when we just had to go from one to another? We actually took what we call the arithmetic mean. So the arithmetic mean is the average that you're used to taking. So really what we did is we took the exact middle number between 5 and 21. So if I do 5 plus 21 and divide that by 2, I get 13. So that's one other way. If you're just missing one value, you can find the arithmetic mean. So what's the arithmetic mean between 14 and 28? Well, 14 plus 28 divided by 2 is 21. So the arithmetic mean is 21. We can do the same thing. 65 plus negative 60 divided by 2 is 5 halves, which we commonly write as 2.5. So the arithmetic mean of 65 and negative 6 is 2.5. Okay, so why do we use these sequences? Well, if we look at this, we talked about the fact that we have this constant change from one term to the next, and we refer to that as a common difference. So instead of talking about it in terms of x, we actually have a variable that we use for that, and that's d, for common difference. And then we have each term, so 5 is the first term, 8 is the second term, 11 is the third term. And that's going to go all the way up to what we call the nth term. So these sub-numbers are really just the number of the term. So a to the a5 is the fifth term. So 1, 2, 3, 4, fifth term. Okay, so how can we use an equation to illustrate this sequence without having to write it out? Well, we can use what's called a recursive formula. So we're going to talk about how do we get to the next term. Well, you take the term you're on, so like the first term, or the second term, let's say. So we start at the second term. So to get to the second term, we have to start with the first term, or we say a sub n minus 1, or the term before, right? So if you're at the second term, minus 1, you go to the first term. If you're at the fifth term, 1 less would be the fourth term. So then we add what we call the common difference. But we need to know where to start, because you can't just add something to nothing. You need to know where you're starting. So we always have to know what that first A1 is. So this recursive formula for 5, 8, 11, 14, 17 would be a sub n equals a sub n minus 1, so this is the previous term, plus 3, where you start a sub 1 with 5. Okay, let's put that into an official form. this is called the recursive definition. So this is what we had in the last slide. And so if we take this, we always start with the first term, and we call that a sub 1 equals some number. And then the recursive formula says, take the previous term, so take the previous term and add the common difference to it. And that's all the recursive formula is. So let's write a recursive formula. So the first thing we need to know is, what is the common difference? And in this case, the common difference is 3, because we're adding 3 to each next term. And then we need to know, well, what was our starting point? So our starting point is always the first term. So a sub 1 here equals 34. And then each term is going to be the previous term plus 3. Because remember, the recursive formula always has two parts. Where do you start, and how are you going to get to the next one? So let's do another one. In this example, the common difference goes from 9 to 4. So if you do 4 minus 9, you get negative 5. So the common difference here, D, is negative 5. And our starting value, the first number, is 9. So a sub 1 equals 9. So to write my recursive formula, a sub 1 equals 9. And then each next term is going to be, or equals, the previous term, a sub n minus 1, minus 5, or plus negative 5. You could write that also. Okay, let's try this one. When we look at this, to go from 1/10 to 5/10, we're going to add 4/10. So the common difference is 4/10. We're always adding 4/10. We're always starting, we started here at 1/10. So a sub 1 is 1/10. And then each term is going to be the term before it plus 4/10. And there's my recursive formula. Here's the general form for all recursive formulas. So go ahead and try these. Welcome back. Here's the answer. Okay, so let's take a look at how this works graphically. If I were to graph the sequence 5, 8, 11, 5 is the first term. So if 5 is the first term, that would be me like saying, go to the first term, right? The first term. So if x equals 1, for say. So if this is n, which remember is the number of terms, so the term number, right? So if this is n equals 1, then I'm at 5. So this would be the value. So this would be the term, right, itself. That says term. There we go. Okay. And so if I plot each of these, we'll notice that we're always going up the same amount and over 1, and that's because we're increasing at a constant rate. And although this is a discrete set, it looks like a linear function. And that's the only difference. A linear function is continuous, where arithmetic sequences are discrete, meaning they don't have any values in between. There's nothing graphed here in between these values. The only values is this point, and this point, and this point. So the next 4 terms, if we had a graph, we could go up 3 and over 1, because we know we're adding 3 each time. So if we start with 5, 8, and 11, and we add 3, so 11 plus 3 would be 14, and then 14 plus 3 would be 17, 17 plus 3 would be 20, and then 20 plus 3 would be 23, and so that would continue forever. Okay, so we talked about the recursive definition. The explicit definition has something to do with the fact that when we graph it, we are looking at a linear function. And in fact, the explicit definition depends on the fact that to get to the nth term, you can use the first term and go up that common difference as many times as you want. And so this is very similar to the slope-intercept form, which remember is y equals mx plus b. This is just adjusted right one. So this is very similar to standard form of a function. Okay, so let's do a couple examples. Now you'll notice that these are the answers to the recursive formulas from the last example. So let's convert these to the explicit form. We notice that in part A, the common difference is 3. So if the common difference is 3, that means the slope on the graph would be 3. And we notice that we're starting at 34. So if a sub 1 is 34, then that means that we're going to go a sub n equals a, which is 34, plus the common difference, which is 3, times n minus 1. And then, of course, we can simplify this because we can distribute the 3. So we have 34 plus 3n minus 3, which we can then write as 3n plus 31. And so a sub n equals 3n plus 31. And you'll notice that the 31 is exactly 3 less than 34 because it's a step back. That's your y-intercept. That would be your 0 term if you had one. Okay, let's try this one. We remember from the recursive definition that our common difference is -5, and our a sub 1 is 9. So let's put that into the explicit formula. Therefore, a sub n equals a sub 1, which is 9, plus -5 times n minus 1. So we distribute the -5, so we have 9 minus 5n plus 5. So a sub n equals -5n plus 14. Okay, let's write the explicit formula for the next one. So the common difference again was 4/10, so d equals 4/10. A sub 1 is 1/10. So if we put that in the formula, we get a sub n equals 1/10 plus 4/10 times n minus 1. And so a sub n equals 1/10 plus 4/10 n minus 4/10. And when we simplify, we get a sub n equals 4/10 n minus 3/10. And so that's our other formula. Okay, so now for each of these, let's go ahead and find the 32nd term. So to find the 32nd term, we can just plug 32 in for n. So that is n equals 32. So a sub 32 is going to equal 3 times 32 plus 31. And so 3 times 32 is 96 plus 31, which is 127. So a sub 32 here equals 127. Okay, let's do the next one. So in this example, a sub 32 is going to be -5 times 32 and then plus 14. And so -5 times 32 is -160, and -160 plus 14 is going to be -146. So a sub 32 equals -146. Okay, last one. So we'll do this one over here since I'm running out of room. So a sub 32 is going to equal 4/10 32, because remember this means n equals 32, so we're just substituting 32 in for n, minus 3/10. So 4/10 of 32 is 12.8, and 12.8 minus 3/10 is 12.5. So a sub 32 in the third case is 12.5. Okay, go ahead and try this one. You're writing the explicit definition and finding the 10th term. I've already written the corresponding recursive definition that you found from the last you try. Okay, welcome back. Here are your answers. Okay, thank you so much for listening. Go ahead and do the 6-1 arithmetic sequences reflection. Up next, we're going to talk about geometric sequences. Have a great day.